Yes, thanks for the introduction. So yeah, I'm Joel Gärtner. I'm a PhD student at KTH, Royal Institute of Technology in Sweden, and we'll be discussing the NTWE problem. And the NTWE problem is a new problem that I've introduced as a natural combination of the NTRU and learning theory problems. And we consider the hardness of this problem both in a provable sense, and as it's a combination of the NTRU and learning theory problems, it's quite natural that it's related. It has some provable relations to the hardness of these problems. But we also consider the concrete hardness of this new problem in a similar way to how the concrete hardness of the learning theory and the NTRU problems are estimated. And finally, we construct and parameterize a NTWE-based crypto system. And in particular, this concrete parameterization has performance that's competitive to that of highly efficient lattice-based crypto systems. And lattice-based cryptography is one of the primary candidates for post-quantum cryptography, with NIST already having selected a lattice-based key encapsulation mechanism and two lattice-based signature schemes to be standardized as post-quantum secure alternatives to the asymmetric cryptography that's being used today. And some of the primary assumptions that are used in lattice-based cryptography are the NTRU and learning theory problems, with both of these problems being very useful and which can be used to construct many interesting crypto systems. But even though these problems are interesting, it's still interesting to, or very useful, it's still interesting to investigate alternative assumptions, which we can base lattice-based cryptography. And as one such problem, we introduced the NTWE problem as a new problem for lattice-based cryptography. And to introduce the NTWE problem, we first introduced some relevant versions of the NTRU and the learning theory problems. And in particular, we consider some structured versions of these problems where we work in polynomial rings. So the elements in these rings are polynomials of degree at most n, and with operations taken modulo the polynomial x to the power of n plus 1, and where n is typically a power of 2. And the module, and we furthermore usually consider this ring taken modulo some integer q, so with the coefficients of the polynomials taken modulo q. And the decision version of the module learning theory problems is to distinguish between two different cases. In both cases, we are given a uniformly random A matrix and a B vector. In one of these cases, this B vector is uniformly random, while in the other case, it's equal to AS plus E for some small secret vector S and some error vector E. And in the rank K instance of this problem, this secret vector S is k-dimensional. The NTRU problem works in similar rings, with an instance being given by a single element in this ring. So in the decision version of this problem, the task is to distinguish between the case where this ring element is sampled uniformly at random and the case where it's equal to G times F inverse for some small elements G and F in the ring. But we can also consider a modular version of the NTRU problem, where we not only are given a single ring element, but instead a matrix in the ring. So the task in the decision version of the module NTRU problem is to distinguish between a H matrix that's either uniformly random or equal to G times F inverse for some matrices G and F that are small in some sense. And the NTWE problem is then a natural combination of the NTRU and the module learning theory problem, with an instance of the problem or an instance of a decision version of the problem being given by an A matrix that's sampled uniformly at random, and a B vector that's either uniformly random or equal to AS plus E multiplied with F inverse for some small vector S, E, and some small polynomial F. And with the task in the decision problem being to distinguish between these two cases. And we have some different reasons to believe that this NTWE problem is hard. We first have some provable hardness guarantees, whereas this NTWE problem is quite similar and the natural combination of NTRU and learning theory problems. We can quite easily see that it's at least as hard as either of these problems, so that's at least as hard as a version of the modular learning theory problem, and at least as hard as a version of the NTRU problem. But we actually expect it to be somewhat harder than we probably can show it to be. And we therefore also consider the concrete hardness of this problem by considering the lattice problem that naturally corresponds to this NTWE problem and estimating the concrete hardness of this NTWE lattice problem. And this is very similar to how the concrete hardness of the NTRU and learning error problems are typically estimated. And for the provable guarantees, we have a very easy to see relation to the modular learning error problem, where we can see if we are given an instance of the modular learning error problem with some A matrix and B vector, then we can simply sample an F polynomial from the correct distribution and produce a correctly formed NTWE instance by multiplying the B vector with this inverse of this F polynomial. And this produces a correctly formed NTWE instance. And as such, if we can solve this NTWE instance, we can solve the original modular learning error problem instance. And as such, we have that the NTWE problem is at least as hard as the modular learning error problem with the same sized A matrix. We also have that the NTWE problem is at least as hard as a version of the NTRU problem, although not the typical NTRU problem, but instead a version of the NTRU problem where we are given multiple samples from an NTRU distribution. So where we're given multiple samples of the GI times F inverse for some fixed denominator F inverse. And this is not the typical way the NTRU problem is usually considered, because usually you're only given a single sample from such an NTRU distribution. But this version with multiple samples from an NTRU distribution has been considered previously and does not seem to be a considerably easier problem than the typical NTRU problem. And if we are given multiple samples from such an NTRU distribution, we can quite easily see that we can use these to construct an instance of the NTWE problem by simply sampling A matrix uniformly at random and using these NTRU samples to construct an NTWE instance, with this NTWE instance having the same denominator, F inverse, as the original NTRU instance. And as such, if we can solve this NTWE instance, we can solve the original NTRU problem, showing that the NTWE problem is at least as hard as this version of the NTRU problem with multiple samples. We also have a relation to from a more structured version of the NTWE problem to a version of the module NTRU problem with rank k+1. And this more structured version of the NTWE problem could potentially be a harder problem than the NTWE problem we actually considered. So this relation does not actually say anything concretely, or it does not guarantee anything about our actual NTWE problem. However, it's more natural to assume that a more structured problem is easier to solve, or at least not a harder problem to solve. And we therefore believe this to be a strong indicator for the NTWE problem in rank K being at least as hard as the module NTRU problem in rank k+1. And this also very closely corresponds to, or more or less exactly corresponds to, the concrete hardness estimate we have for the NTWE problem. And for the concrete hardness estimate of the NTWE problem, we use that the NTWE problem naturally corresponds to a lattice problem, where the task is to recover an unusually short vector in a special type of lattice. And this is essentially exactly the same lattice problem as what's typically considered for the NTRU and learning error problems, as both of these problems can be interpreted as similar lattice problems. And in particular, the NTWE problem in rank K is the corresponding lattice problem is essentially the same as the lattice problem in a module NTRU problem for rank k+1. Which is exactly what the relation between the more structured NTWE problem and the modular NTRU problem was on the previous slide. We also have that the NTWE problem in rank K, the corresponding lattice problem is very similar to the lattice problem in a modular learning error problem instance of rank k+1. And this modular learning error problem in rank k+1 is a significantly harder problem than the modular learning error problem in rank k for the parameters we consider, because we usually consider the rank k to be quite small, usually less than 5. So there's a significant difference between the modular length error problem in rank k and rank k plus 1. And so this concrete hardness estimate is that the NTWE problem is quite a lot harder than we probably could relate it to. Probably could relate to the modular length error problem. And for the actual the concrete hardness estimates for this NTWE problem, or for the corresponding lattice problem, we use that these types of lattice problems have been investigated extensively due to their relevance for parameterizing NTRU and NTWE-based crypto systems. So we can make use of essentially the same type of analysis of lattice algorithms to parameterize our crypto system. And this is just a short subset of works which have studied these types of problems. And we also consider and construct a NTWE-based crypto system. So in this crypto system, the public key consists of essentially consists of an NTWE instance with a uniformly random A matrix that's k times k minus 1 dimensional. And assuming the computational indistinguishability of this public key from uniformly random, we then have that the ciphertext essentially corresponds to k samples from a modular length error instance of rank k plus 1, or of rank k, with the message encoded into one of these samples, and thus assuming the computational hardness of the decision version of the modular length error problem, we have that the message is hidden in this ciphertext. Decryption then follows from this formula, where we have that we have correctness due to the fact that in this inner parenthesis, we remove the dependence on the A matrix, and all remaining terms that do not depend on the message are expected to be small with high probability and are therefore rounded away in the following operations. And to actually recover the message, we then have to multiply with F2 inverse, where F2 is the polynomial F evaluated in the ring R2, so with the coefficients taken modulo 2 instead of modulo Q, and with the inverse taken in this ring as well. And this NTWE-based crypto system is very similar to a comparable modular length error-based crypto system with similar public key and decryption and the same type of ciphertext, but with some differences. In particular, for comparable security level, a modular length error-based crypto system would require an A matrix that's a square matrix that's k times k dimensional, and with the public key consisting of a modular length error instance of rank k. And the ciphertext then consists of k plus 1 samples from a modular length error distribution of rank k with the message encoded, and with decryption in this modular length error-based crypto system being correct due to a similar argument regarding the smallness of everything that does not depend on the message. And as our NTWE-based crypto system is quite similar to a comparable modular length error-based crypto system, we can make many of the same choices when we parameterize our crypto system. And in particular, we consider a parameterization that's very similar to the Crystal-Kyber submission to the NIST post-quantum standardization process, which has already been selected to be standardized. So in particular, we consider the same ring and modulus as in Crystal-Kyber, and with the distribution for the secret vector S and error vector E that are very similar to the corresponding parameterizations of Crystal-Kyber. And but a significant difference between our scheme and Crystal-Kyber is that we use a smaller A matrix for a comparable security level due to our estimated concrete hardness for the NTWE problem. And as such, we have to perform fewer operations as we have a smaller matrix, which we have to perform multiplications with. And essentially all the operations or the operations in our crypto system have essentially the same efficiency as for Crystal-Kyber. So as we have to perform fewer operations of essentially the same cost, our crypto system is somewhat more efficient than Crystal-Kyber. So for these concrete parameterizations here, some examples. We have that for a smaller A matrix, we have essentially the same estimated core SVP security, which is a conservative estimate for the bit security of lattice-based crypto systems. We also have essentially the same sized public key, which may seem surprising since the A matrix was part of the public key and we used a smaller A matrix. But in both Kyber and in our scheme, we do not actually use a uniformly random A matrix, but instead use a pseudo-randomly generated A matrix, which can be derived from a small seed. So the public key does not only have to contain this small seed. We also have that both our crypto system and Crystal's Kyber has a small probability of incorrectly decrypting the messages. But this decryption failure probability is small in both of the schemes and quite comparable between the two different schemes. We also have that the ciphertext size for our crypto system and Crystal's Kyber is quite similar, which may also sound surprising, as in our crypto system we only have K ring elements as the ciphertext, while Crystal's Kyber, or a comparable modular internet-based crypto system, requires K+1 ring elements for the ciphertext. But this difference is due to the fact that for modular learning theory-based crypto systems, one can perform some quite heavy ciphertext compression, which allows the K+1 ring elements that the ciphertext actually consists of to be represented in essentially as much space as K ring elements. And as such, our crypto system and Crystal's Kyber have essentially the same sized ciphertext. However, there are certain applications where this ciphertext compression is not applicable and where you cannot use it. And for these types of schemes, our crypto system actually has significantly smaller ciphertext than a comparable modular learning theory-based crypto system. Furthermore, the fact that we do not use this ciphertext compression allows our scheme, or is an additional reason for why our scheme is somewhat more efficient than Crystal's Kyber, as this allows the ciphertexts to be transmitted in the same form as we operate on them. Because in a Crystal's Kyber, we have to perform a inverse transform, or we have to transform the ring elements during encryption and decryption in order to perform the ciphertext compression. And so I mentioned that the operations we performed in our scheme are of essentially the same cost as in Crystal's Kyber. And this is due to our scheme and Crystal's Kyber both using the number theoretic transform in order to allow efficient multiplications. And this number theoretic transform also allows this inverse, which is new in our scheme compared to Crystal's Kyber, to be computed in essentially the same cost as multiplication. And as we use a smaller A matrix, the cost of this additional inverse operation and multiplication with this F inverse is more than compensated for during key generation. We do, however, have that the multiplication and inversion in R2 during decryption cannot be performed using the same number theoretic transform. And this can be a quite costly part of our crypto system, but this can be alleviated by sampling the F polynomial from a distribution such that it is trivial in R2, so that we do not have to perform this inverse in R2, and do not have to perform this multiplication. And then the decryption only consists of similar operations as in comparable modular learning theory-based crypto system, although this comes at the cost of a somewhat larger decryption failure probability. But this was already accounted for in the concrete parameterizations I presented in a few slides ago. So for the parameterizations in those scheme in that slide, our scheme is actually more efficient in all steps than in comparable Kyber parameterizations. And in conclusion, we have introduced the NTWE problem with provable relations to both the NTRU and learning theory problems, as it is a natural combination of these problems. We have also considered the concrete harness of this NTWE problem by noting that it naturally corresponds to a lattice problem, and estimated the harness of this lattice problem in a similar way to how the concrete harness of the NTWE of the NTRU and learning theory problems are typically estimated. And finally, we have also constructed the NTWE-based crypto system and considered a concrete parameterization of this system with its performance being competitive with that of highly efficient lattice-based crypto systems, such as Crystal's Kyber, which is about to be standardized by NIST. So, thank you. Any questions?
questions?
Thanks for your talk. So correct me if I'm wrong, but so let's say like one of these assumptions is broken, like NTRU or LWE. So is it the case that NTWE gets broken as well, or?
It's not guaranteed. So there is the possibility that one of the assumptions is broken, but none of the other are broken. But it seems like all of the assumptions are essentially equivalent. All of them are based on, or the current approach of solving all of these problems is the same, that solving the natural lattice problems are very similar. And but there is no guarantee that if a NTRU-based crypto system is broken, that a learning to error-based crypto system is broken, or that our crypto system is broken, or any way like that.
But I mean, in a hypothetical world where some attack algorithm specifically exploits NTRU, and I'm just like speaking hypothetically, then this hypothetical attack on NTRU, which does not affect LWE, so it will affect NTWE as well.
Not guaranteed.
Okay.
And I find that to be a potentially interesting thing with this. So for example, we have the overstretched NTRU parameters, which is if you choose the modulus Q to be way too large, then the NTRU problem becomes easy. But similar parameters do not seem to be applicable to the learning to error problem. And I find it potentially be interesting to investigate if some of these intermediate problems, like the NTWE problem, is vulnerable to the overstretched parameters or not. And it's a non-trivial question, I believe.
Okay, thank you very much.
Any other questions?
Thank you for your talk. So I have a question on the parameter selection. Could you explain a little bit why you can have a smaller matrices than Kyber? Is that because you have the actual F?
Why a smaller decryption failure problem?
No, why you have a smaller matrices?
Smaller matrices.
Right.
Because if you consider the naturally corresponding lattice problems, we have this F inverse multiplication as well, and that is also included in the corresponding lattice problem. So the naturally corresponding lattice problem is essentially a combination of a NTRU lattice and a learning to error lattice, and we get some hardness from both of those. So we have a smaller S, but have a F part as well.
Okay, thank you.
So following up on that question, the connection between your problem, so the NTWE at K versus like K+1 for these other problems, that's based off of connecting it to this lattice problem. It's not a direct proof of that fact?
Yeah, besides the more structured version of the NTWE problem to the modular entry problem of rank K+1, that's a provable thing. And it's similar to, so you can say that the ring learning to error problem is a inhomogeneous version of the NTRU problem. And in a similar way, we can say that the NTWE problem is a less structured version of the modular entry problem in rank K+1 or so.
Okay, thank you.
So if not, maybe I ask one question. So can you use the same idea to signatures? Or you talk about the encryption.
So you can use similar ideas for signatures. I haven't looked that much into it, but you can do some these fiat Shamir with aborts type of signatures. But I'm not sure if you gain any significant advantages compared to the learning to error-based or NTRU-based signatures.
Okay. Also, can this construction used for fully homomorphic encryption just like LWE does, or it's something different?
That's a good question I haven't actually considered, but I would expect it to be possible in some sense, but I'm not sure.
Any other question? Okay, if not, let's thank the speaker again, please. So we'll end our